Welcome to this tutorial on speeding up Simulink. In this session, we will introduce best practices for modeling in Simulink. There are several best practices that can enhance simulation performance. In this session, we will focus on two of them: avoiding the use of certain Simulink blocks that can slow down simulations, and eliminating algebraic loops, which can adversely affect both speed and stability. Some Simulink blocks rely on interpreted code, which can negatively impact simulation runtime performance, especially in the default gyre accelerator mode. When a model contains a significant number of these blocks, the performance benefits of running in accelerator mode may be minimal. Let's use the scope block as an example to demonstrate this. We will compare the simulation performance of the scope block with the data inspector in Simulink for visualizing data, highlighting the performance differences and potential benefits of using the data inspector. In this example, we use a scope block to log and visualize a single signal. To evaluate the simulation performance, we enable the Simulink profiler to measure the time spent during the simulation. From the results of the profiler, we observe that the scope block accounted for approximately 3.8 seconds out of the total 130 seconds of simulation time, highlighting its impact on performance. Next, we comment out the scope block and use the data inspector to log and visualize the same signal instead. As observed, using Data Inspector saved approximately 2 seconds of total simulation time in this example, demonstrating its efficiency compared to the scope block. This chart summarizes the simulation performance comparison between the scope block and the Data Inspector. Next, we will discuss how to eliminate algebraic loops. We will demonstrate this using a simple example that includes a feedback control loop, consisting of a gain block and a transfer function block. First, we run the model that does not contain an algebraic loop and log the time spent during the simulation. Next, we create an atomic subsystem containing the gain block and the transfer function block, which introduces an algebraic loop into the model. Simulink can still run the simulation properly despite the algebraic loop, though it triggers a warning message. However, the simulation time has increased significantly, about 4 times longer than the previous model without the algebraic loop. To resolve the algebraic loop, we can start by enabling the Minimize Algebraic Loop Occurrences option in the Block Parameters panel of the atomic subsystem. As observed, this method brings the simulation time back to a level similar to the model without the algebraic loop. Another common method to eliminate an algebraic loop is by adding a delay block in the loop. After running the simulation, we observe that the time spent is similar to the previous solution. However, when examining the simulation result in the top right corner, we can see that adding a delay block in the loop causes instability in the dynamic system. This serves as a counterexample, demonstrating that adding a delay block to eliminate an algebraic loop does not always work and can be risky, as it introduces instability in the dynamic system. To resolve the instability issue, we can replace the delay block with a high-pass filter block in the loop. The simulation results show that the system behaves correctly, and the performance is similar to previous simulations, maintaining the same simulation speed. In addition to avoiding specific Simulink blocks and eliminating algebraic loops, there are other best practices to explore for improving simulation performance. These include leveraging the model operating point for faster startup simulations, minimizing unnecessary signal logging, closing unused visualizations during simulations, using sample times that are multiples of each other, and more. Are there even more techniques to enhance simulation performance by improving the model? Stay tuned for the next session.